Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Andrew Granville, A Life in Elementary Elegance. Consider the integers. These fundamental building blocks of mathematics, seemingly simple in their startness, harbor depths of complexity that have captivated mathematicians for millennia. Within this seemingly straightforward realm, Andrew Granville has carved a unique niche, a career defined by relentless pursuit of elegance and a profound skepticism toward unnecessary complexity. His approach, which he might playfully term pretentious, is a testament to the power of directness in a field often characterized by intricate analytical machinery. Granville's work is a philosophy, a sustained argument for the inherent beauty and surprising power of elementary methods in analytic number theory. The late 20th century witnessed a flourishing of sophisticated techniques, often drawing heavily on the tools of complex analysis. These methods, while undeniably powerful, sometimes obscured the underlying simplicity of the relationships between numbers. They could feel like navigating a labyrinth when a direct path might exist. Granville, however, champions an approach that favors clarity and directness, a pursuit of the most fundamental structures governing the behavior of integers. This pursuit manifests in a central concept, a guiding principle that permeates his work, the notion of pretentiousness. This captures the essence of his approach. Granville's pretentiousness principle, in essence, explores the limitations of certain functions in mimicking others. A multiplicative function, a function that respects the multiplicative structure of the integers, cannot simply pretend to behave like a function of the form n to the power of it, where I is the imaginary unit and t is a real number. This seemingly simple idea, however, has profound implications for understanding the distribution of prime numbers and other fundamental aspects of number theory. It is a sharp tool capable of dissecting complex behavior and revealing underlying patterns. Granville's approach reveals profound truths through simple means. His reservations about elaborate methodologies or call for discerning use, not a rejection of powerful techniques. He advocates for methods that illuminate the core structures of integers, revealing underlying logic without obscuring it in abstraction. This quest for clarity, for the inherent beauty in simple representations, is a strategic choice, not a mere aesthetic preference. Focusing on elementary methods allows Granville a deeper, more intuitive understanding of the problems he addresses. This enables a more direct engagement with the fundamental properties of numbers, leading to insights hidden behind complex analysis. His methods are often characterized by ingenuity and resourcefulness, employing combinatorial techniques and clever arguments to achieve remarkable results. Granville's work extends beyond pure mathematics, impacting cryptography and computational number theory. The nature of primality testing is deeply intertwined with the behavior of functions and their ability to mimic other functions. Granville's work has illuminated the limitations of certain primality tests, contributing to more robust and reliable methods. Granville's career is a systematic dismantling of unnecessary complexity in number theory, a continuous refinement, progressively stripping away layers of abstraction to reach the essential core of mathematical relationships. This direct approach, focused on the fundamental structures of integers, makes his contributions unique and enduring. True elegance in mathematics often lies in simplicity, in the ability to reveal deep truths through clear and insightful methods. This commitment to elementary elegance will form the foundation of our examination of his remarkable contributions. The journey ahead will reveal the profound impact of Granville's work, from his early investigations into the intricacies of primality to his ongoing engagement with some of the most challenging problems in modern number theory. The pursuit of prime numbers, those integers divisible only by one in themselves, has captivated mathematicians for millennia. Central to this fascination is the problem of primality testing. How can one efficiently determine whether a given number is prime? Early approaches relied on trial division, systematically checking for divisibility by smaller numbers. This method becomes computationally infeasible for large numbers, rendering it impractical for modern applications like cryptography. Fermat's Little theorem offers a more sophisticated approach. It states that if p is a prime number, then for any integer a, the number to the power of p minus a is an integer multiple of p, expressed mathematically to the power of p minus s congruent to 0 modulo p. This theorem suggests a potential primality test. Choose a random integer a, compute it to the power of n modulo n, where n is the number being tested. If the result is congruent to modulo n, then n is likely prime. However, this test is not without limitations. Composite numbers, those with factors other than 1 and themselves, can sometimes pass this test for certain choices of r. These deceptive numbers are known as pseudoprimes, or more specifically, Fermat pseudoprimes to the base a. A particularly insidious class of pseudoprimes are Carmichael numbers. These are composite numbers n that satisfy Fermat's Little theorem for every integer that is relatively prime to n. In other words, they are numbers that consistently misrepresent their primality, regardless of the chosen base. The existence of Carmichael numbers poses a significant challenge for primality testing. Since they satisfy Fermat's Little theorem, a simple application of this theorem will incorrectly identify them as prime. This raises a fundamental question: how common are Carmichael numbers? Do they occur frequently enough to undermine the reliability of Fermat-based primality tests? For many years, mathematicians suspected that infinitely many Carmichael numbers existed, but a proof remained elusive. The difficulty lay in the seemingly random distribution of these numbers, making it difficult to establish any predictable pattern or recurrence. It was in this context that Andrew Granville, along with William Alford and Carl Pomerance, made a groundbreaking contribution. In their seminal 1994 paper, Alford, Granville, and Pomerance proved that there are indeed infinitely many Carmichael numbers. Their proof, surprisingly, relied on elementary and combinatorial arguments, avoiding the use of advanced analytical techniques or unproven hypotheses. This approach underscored Granville's dedication to uncovering deep truths through accessible methods. The key idea behind their proof involves constructing Carmichael numbers with specific properties. A Carmichael number must be square-free, meaning it is not divisible by any perfect square greater than 1. Each prime factor p of a Carmichael number n must satisfy the condition that p minus 1 divides n minus 1. This condition ensures that Fermat's Lowell theorem holds for all bases are relatively prime to n. Alford, Granville, and Pomerance skillfully utilized these properties to construct an infinite family of Carmichael numbers. They commenced by selecting a set of primes satisfying specific congruence conditions. These conditions guaranteed that the product of these primes would be a Carmichael number. By carefully choosing the primes, they were able to ensure that the resulting Carmichael number satisfied all necessary criteria. The brilliance of their proof lies in its combinatorial nature. They demonstrated that it is always possible to find a set of primes satisfying the required congruence conditions, regardless of the desired size of the Carmichael number. This implies that there is no upper limit of the size of Carmichael numbers, and therefore there must be infinitely many of them. Their proof is a testament to the power of elementary methods in number theory. By focusing on the fundamental properties of Carmichael numbers and employing clever combinatorial arguments, they resolved a long-standing open problem. Their work significantly impacted the field of primality testing, highlighting the limitations of Fermat-based tests and motivating the development of more robust algorithms. The discovery that infinitely many Carmichael numbers exist has profound implications for cryptography. Many cryptographic systems rely on the difficulty of factoring large numbers into their prime factors. Primality tests are used to generate large prime numbers, which are essential for these systems. If a primality test misidentifies a Carmichael number as prime, it could create a system vulnerability. The work of Alford, Granville, and Pomerance serves as a cautionary example, reminding us that even seemingly reliable primality tests can be misled by deceptive numbers. This underscores the importance of rigorous mathematical analysis and the need for robust algorithms that can withstand the challenges posed by Carmichael numbers and other pseudoprimes. Granville's contribution to proving the infinitude of Carmichael numbers exemplifies his approach to number theory, a focus on elementary methods, a commitment to clarity, and a willingness to tackle challenging problems directly. This work solidified his reputation as a leading figure in the field and paved the way for many subsequent advances in primality testing and factorization. The discovery of infinitely many of these liar numbers necessitated a reevaluation of existing primality tests and spurred the development of more sophisticated techniques. This contribution stands as a cornerstone in the ongoing quest to distinguish primes from composites with absolute certainty and efficiency. The quest to distinguish primes from composites, a relentless pursuit throughout the history of mathematics, faced a significant hurdle: the development of a truly reliable primality test. While probabilistic methods offered speed, they carried the inherent risk of error, a vulnerability underscored by the existence of Carmichael numbers. These pseudoprimes, deceptively composite, could pass tests designed to identify primes, highlighting the need for a deterministic algorithm, one that would guarantee a correct answer every time. This requirement was a challenge that occupied mathematicians for decades, and the solution, when it arrived, was nothing short of revolutionary. In 2002, Manindra Agrawal, Neeraj Kale, and Nitin Saxena, collectively known as AKS, presented a groundbreaking primality test. Their algorithm, a deterministic polynomial time algorithm, fundamentally altered the landscape of computational number theory. The problem, a long-standing question in computational complexity, was this: is primality testing in P, the class of problems solvable in polynomial time? The AKS algorithm provided an affirmative answer, demonstrating that primality testing could be performed efficiently, a result of profound theoretical and practical significance. The AKS algorithm's initial publication in the journal Annals of Mathematics was, to put it mildly, dense. The paper, filled with intricate arguments and complex notation, presented a considerable hurdle for many mathematicians. Understanding the core ideas, the elegance of the approach, and the implications of the result required a substantial investment of time and effort. The importance of the discovery, however, was immediately clear to those who could navigate its complexities. Andrew Granville, already a prominent figure in number theory, recognized the profound significance of the AKS primality test immediately. He understood that the algorithm, if its core principles could be distilled and disseminated, would transform the field. Its contribution, therefore, was as its foremost interpreter, clarifier, and champion, rather than as an author of the original paper. He saw the potential for this work to become a cornerstone of number theory and computer science, a result that would be taught for generations. Granville, along with Carl Pomerance, undertook the task of simplifying and clarifying the AKS algorithm. Their collaborative effort resulted in a seminal paper titled "It is Easy to Determine Whether a Given Integer is Prime." This title, a clever play on the perceived difficulty of the subject, served as a clear statement of the algorithm's accessibility. The paper offered a more streamlined and accessible exposition of the AKS algorithm, breaking down its complex arguments into more manageable steps. It provided a path for other mathematicians to understand and appreciate the algorithm's underlying principles. The impact of Granville's work alongside Pomerance's, was immediate and widespread. A simplified exposition made the AKS algorithm accessible to a broader audience, enabling researchers to build upon its foundations. Students and academics alike could now grasp the core concepts without becoming lost in the intricate details of the original paper. The clear presentation accelerated the dissemination of the algorithm, encouraging its adoption and further investigation. The modern relevance of the AKS primality test and Granville's role in its popularization is undeniable. The algorithm, a foundational result in computational complexity, is taught in computer science and number theory courses worldwide. It provides a theoretical benchmark for primality testing, establishing that the problem is solvable in polynomial time. While practical implementations of the AKS algorithm have been refined over the years, the theoretical significance of the original result remains paramount. Granville's contribution extended beyond clarifying the algorithm. He played a crucial role in contextualizing the AKS work, highlighting its implications for other areas of number theory and computer science. He explained the algorithm's relationship to existing primality tests, demonstrating its advantages and limitations. He also explored the potential of the AKS algorithm to address other open problems in the field, increasing its impact and influence. His actions exemplify the role of a scholar to generate original research and foster understanding and promote the dissemination of knowledge. Granville's work on the AKS primality test serves as a model for translating complex mathematical ideas into accessible and influential contributions. He transformed a brilliant but challenging paper into a cornerstone of the field, ensuring its enduring legacy. His efforts helped to solidify the importance of the AKS algorithm and its place in the history of mathematics, ensuring that the ideas of Agrell, Kale, and Sixiner would be understood and appreciated by generations of mathematicians. This instance demonstrates Granville's ability to identify and champion significant mathematical breakthroughs. His work highlights his capacity to grasp the broader context, recognize the significance of intricate concepts, and make them understandable to others. His work with the AKS algorithm, therefore, is an act of intellectual leadership, a testament to the power of clear communication and the importance of sharing complex ideas with the wider mathematical community. The legacy of the AKS primality test and Granville's contribution to its understanding and dissemination continues to resonate today. It serves as a reminder that even the most intricate mathematical ideas can be made accessible through careful explanation and dedicated effort. The work stands as a testament to the power of collaboration and the enduring value of deep understanding in advancing the frontiers of mathematical knowledge. The AKS algorithm, now a standard tool in the mathematician's arsenal, is a direct outcome of the combined efforts of the original authors and those, like Granville, who worked to make it understood. The algorithm's place in the history of mathematics and Granville's role in its success are secure. Granville's work encompasses a remarkable ability to discern the underlying connections between seemingly disparate challenges within number theory. This is particularly evident in his profound engagement with the ABC conjecture. The ABC conjecture, a remarkable assertion proposed by Masser and Easterley, offers a strikingly simple yet profoundly powerful unifying principle. It suggests a connection between the size of the terms in a Diophantine equation and the factors that compose them. While the conjecture remains unproven, its implications reverberate throughout the field of number theory, revealing hidden relationships between seemingly isolated problems. Granville focused on mapping the conjecture's consequences. His contributions lie in the meticulous exploration of the conjecture's potential to resolve numerous Diophantine problems. He meticulously demonstrated how the truth of ABC would systematically resolve a remarkable array of challenges. This approach, treating the conjecture as a potent tool, stands as a testament to his insightful understanding of the field's intricate structure. Consider the profound implications of this approach. The conjecture, if true, would provide a framework for understanding the intricate relationships between the sizes of integers and their factors. This framework would unveil connections between problems that had previously appeared disconnected, providing a unified perspective on a vast landscape of Diophantine equations. Granville's work serves as a beacon, illuminating the potential for a unified theory to encompass a wide range of seemingly isolated problems. In his exploration of the ABC conjecture's consequences, Granville meticulously examined its potential impact on various Diophantine equations. He meticulously charted the path towards a deeper understanding of these equations, demonstrating how the conjecture's truth would unveil previously hidden relationships. His work provides a roadmap, guiding future research and highlighting the conjecture's enduring importance. His profound understanding of the intricate connections within number theory is evident in his ability to discern the broader implications of the ABC conjecture. He considered the broader landscape, recognizing the potential for a unifying principle to connect a vast array of challenges. This perspective allowed him to identify and highlight the significance of the conjecture's potential to resolve a wide range of issues. Through his meticulous analysis, Granville elucidated how the ABC conjecture could systematically resolve numerous Diophantine problems. He demonstrated this potential, offering a clear path forward for researchers interested in these profound areas of mathematics. His work is a profound demonstration of the power of a unified approach to complex mathematical problems. The implications extend well beyond pure mathematics. If proven true, the ABC conjecture would have profound implications for our understanding of the the distribution of prime numbers and the properties of integers. Granville's work helps us appreciate the potential for a deeper understanding of the fundamental structures of numbers by mapping these consequences. His work has profoundly influenced the direction of research into Diophantine analysis. His insights into the conjecture's consequences have inspired generations of mathematicians to explore its potential, contributing to a richer understanding of the field. He studied the broader structure, the underlying architecture of the field, rather than merely individual equations. This insightful approach has significantly shaped the trajectory of research in Diophantine analysis. His profound understanding of the field's interconnectedness and his ability to identify unifying principles have cemented his position as a leading figure in the advancement of number theory. His meticulous mapping of the ABC conjecture's consequences has become a cornerstone of modern Diophantine analysis, guiding and inspiring researchers for years to come. His influence is palpable, and his work continues to inspire fresh perspectives and innovative approaches to complex problems. A new probabilistic lens emerged in the landscape of analytic number theory, a powerful shift driven by the groundbreaking collaboration between Andrew Granville and Soundararajan's partnership illuminated pathways previously obscured by the formidable Generalized Riemann Hypothesis, a cornerstone conjecture whose unproven nature had often hindered progress in understanding the distribution of primes and the intricate behavior of L functions. The challenge lay in achieving profound, unconditional results within a field steeped in deterministic approaches. The innovative solution, a paradigm shift, involved embracing probabilistic and statistical models to study these fundamentally deterministic objects. The core of their approach was to treat these objects as if they were random variables. This seemingly paradoxical maneuver opened doors to a new realm of possibilities. By analyzing the distribution of character sums and L functions through a probabilistic lens, they could identify hidden patterns and biases, revealing profound insights into their structure. The fruits of this probabilistic perspective were substantial, yielding deep, unconditional theorems about the biases and distributions of these objects. This innovative perspective became a powerful toolkit, enabling the field to circumvent the generalized Riemann hypothesis obstacle in countless situations. Consider, for instance, the intriguing phenomenon of Chebyshev's bias, a subtle yet persistent tendency observed in the distribution of primes. This bias, seemingly defying simple explanations, was illuminated by the Granville-Soundararajan framework. By modeling primes as possessing probabilistic characteristics, they were able to uncover the underlying reasons behind this bias, demonstrating how these probabilistic models could reveal hidden structures within the seemingly chaotic distribution of primes. The implications of this probabilistic approach extended far beyond the specific problems they addressed. It introduced a new perspective, a fresh way of thinking about deterministic mathematical objects. This novel perspective allowed for deeper exploration of the hidden connections and structures within number theory. This was a recognition of the potential for probabilistic insights to illuminate even the most fundamentally deterministic mathematical realms. This innovative approach provided a pathway for exploring the intricate relationship between randomness and order within the seemingly fixed structure of prime numbers. It was a testament to the power of adopting a fresh perspective, a willingness to explore uncharted territories, and a profound understanding of the interconnectedness of seemingly disparate mathematical ideas. The Granville-Soundararajan collaboration was a fundamental shift in the way mathematicians approached the field. Their work highlighted the inherent power of probabilistic models to reveal hidden structures and patterns. It demonstrated that even in the seemingly rigid world of number theory, probabilistic tools could offer a powerful new perspective, allowing for the exploration of previously inaccessible realms. This approach was a complement, a new tool in the mathematician's arsenal. It allowed for a richer, more nuanced understanding of the objects under study, unveiling hidden biases and patterns that had remained unnoticed before. The impact of this collaboration reverberates throughout the field of analytic number theory. Mathematicians were inspired to explore the potential of probabilistic models, leading to a surge in research and a more comprehensive understanding of the intricate relationships between primes, character sums, and L functions. The Granville-Soundararajan approach became a foundational pillar for subsequent research, fostering a new generation of number theorists who embrace this innovative perspective. This probabilistic framework proved remarkably effective in tackling numerous problems that had resisted conventional methods. It spurred a new generation of research, encouraging mathematicians to explore the interplay between randomness and order within number theory. The approach was a philosophical shift, a paradigm shift in the way mathematicians view the objects and structures of the field. The insights derived from this collaboration extended beyond the realm of number theory. The principles and techniques developed in this partnership found applications in other areas of mathematics and beyond. The ability to model seemingly deterministic objects through a probabilistic lens has profound implications for understanding complex systems in diverse fields, from physics to finance. This approach offered a powerful new tool for unraveling the intricate dynamics of the natural world. Their work was a paradigm shift, a new way of seeing the world of numbers, demonstrating the power of combining seemingly disparate perspectives, bridging the gap between the deterministic and the probabilistic. The Granville-Soundararajan collaboration served as a catalyst for new explorations, transforming the landscape of analytic number theory. It was a testament to the power of collaboration and the enduring value of embracing innovative approaches to complex problems. Granville's influence extends far beyond the realm of rigorous mathematical proofs. His profound impact lies in his exceptional ability to illuminate complex concepts, fostering a profound appreciation for the beauty and elegance inherent within number theory. This section explores the expository and mentoring aspects of his career, showcasing how he has shaped the pedagogy of modern number theory, guiding generations of scholars towards a deeper understanding of this captivating field. His books, such as Prime Number Races, are compelling narratives that weave together historical context, intuitive explanations, and profound insights. He masterfully frames complex mathematical ideas as answers to intriguing questions, drawing readers into the very heart of the subject matter. This approach is deeply rooted in Granville's understanding of the inherent human drive to uncover foundational truths. The narrative structure is the very essence of his approach. He meticulously connects seemingly disparate concepts, highlighting the underlying threads that unify the field. This approach invites readers to actively participate in the exploration of mathematical ideas. This active participation fosters a deeper understanding and a stronger appreciation for the subject's beauty. Granville's expository style is about evoking a sense of wonder. He understands that mathematics is a vibrant field filled with surprising connections and profound insights into the nature of numbers. His writing is imbued with a sense of excitement, encouraging readers to engage with these ideas as active participants in a grand intellectual quest. This narrative approach is further amplified in his teaching. Granville's lectures are dynamic explorations of mathematical ideas. He skillfully weaves together historical context, intuitive explanations, and motivational discussions, fostering an environment where students feel empowered to engage with the subject on a deeper level. He encourages them to ask why, rather than simply how. This emphasis on the why is fundamental to his pedagogical philosophy. He recognizes that understanding the motivation behind a theorem is crucial for truly grasping its significance. This approach reveals an understanding of the human mind and its inherent desire to understand the underlying principles driving the universe. His mentorship shapes the careers of numerous leading number theorists. He is a staunch believer in fostering collaborative environments, encouraging open discussions, and the exchange of ideas. He recognizes that the insights of a collective mind are often greater than the sum of its individual parts. His mentorship is about nurturing intellectual growth and fostering a sense of community within the mathematical world. Granville's pedagogical approach clearly impacts his students' work. His students are thinkers, explorers, and innovators, not simply trained mathematicians. They grasp the field's history, underlying principles, and the inherent beauty of mathematical ideas, not just techniques. This cultivation of critical thinking, rather than rote memorization, defines his mentorship. His influence extends beyond number theory. His emphasis on narrative, intuition, and foundational thinking provides a strong counterpoint to the increasing abstraction in many mathematical fields. This focus on clarity and accessibility ensures the study of whole numbers remains grounded in a search for elegant, understandable structure. His work powerfully demonstrates that mathematical rigor and profound insights can coexist, creating a truly engaging and enriching learning experience. Granville's impact extends beyond his students' technical skills. It shapes their approach to mathematics. He fosters a love for the subject, a sense of wonder, and a deep understanding of its underlying principles. This legacy will continue to influence the field for generations. He has inspired a generation of mathematicians to pursue their intellectual journeys with passion and enthusiasm, not merely taught number theory. Andrew Granville's career, a symphony of meticulous research and passionate advocacy, represents a fundamental shift in the practice of number theory. He champions a philosophy, a method, and a way of approaching mathematical truth that is profoundly inspiring, not merely effective. He has demonstrated that elementary equates to fundamental and not easy. His work, from the seemingly pretentious principle to the meticulous clarification of the AKS primality test to the mapping of the ABC conjecture, constitutes a unified campaign, a relentless pursuit of the most direct, intuitive, and foundational path to understanding. Granville's dedication to clarity and accessibility has resonated deeply within the mathematical community, offering a compelling perspective on modern mathematical discourse. He has shown that mathematical rigor and profound insights can be powerfully integrated into an approach that is both intellectually stimulating and profoundly engaging. His emphasis on narrative, intuition, and foundational thinking has instilled in his students and colleagues a profound appreciation for the intrinsic beauty and elegance within the study of whole numbers. This is a profound engagement with the very essence of mathematical truth. His work has fostered a deep appreciation for the subject's inherent elegance and beauty. Through his meticulous exploration of the intricate relationships within the realm of whole numbers, Granville has ignited a passion for the subject in countless minds. This passion, this profound engagement, is the true legacy of his work. It is a fundamental shift in perspective, a re-evaluation of the very methodology employed in the pursuit of mathematical understanding. Consider the pretentious principle, a seemingly provocative concept, yet one that embodies Granville's deep-seated belief in the power of intuition and foundational understanding. He sought to unravel the underlying assumptions, to expose the fundamental principles that underpin seemingly complex results. This relentless quest for foundational understanding is evident in his work on the AKS primality test, a monumental achievement that clarified and simplified a crucial aspect of computational number theory. He offered a profound reevaluation of the very question itself. Similarly, his work on the ABC conjecture exemplifies his dedication to finding the most direct and intuitive path to understanding. He has illuminated the underlying narrative, revealing the profound beauty and elegance inherent in the relationships between integers. This commitment to clarity and accessibility has had a profoundly positive impact on the field, encouraging a more intuitive and narrative-driven approach. Granville's works impact extends beyond the technicalities of number theory. He has fostered a deep appreciation for the inherent beauty and elegance within the subject, inspiring a new generation of mathematicians to embrace the power of intuition and foundational thinking. His emphasis on narrative and clarity has transformed the very landscape of mathematical research and learning, creating a more engaging and enriching experience for all. Granville's legacy is about the profound shift he has instigated in the very approach to mathematics. He has demonstrated that an elementary approach, one grounded in fundamental principles, can be profoundly profound and enriching. This is a legacy that will continue to shape the field for generations to come, ensuring that the study of whole numbers remains grounded in a search for elegant, comprehensible structure. He has taught number theory, inspiring a generation of mathematicians to pursue their own intellectual journeys with passion and enthusiasm. His influence extends beyond mathematical technique. It permeates the very spirit of mathematical inquiry. This is a legacy that transcends the specific problems he tackled. It is a legacy of intellectual rigor, coupled with an unwavering commitment to clarity and accessibility. Granville's work stands as a beacon, a testament to the power of intuition, narrative, and foundational thinking in the pursuit of mathematical truth. He has shown us that the most profound insights can often be found in the most elementary of principles. His influence on the field is undeniable, and his legacy will undoubtedly inspire generations of mathematicians to come. This work holds immense intellectual value.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.